So for me, to do science, I need space to be able to set out my instruments. So to find anywhere where there's space is really hard.
Digging up some farmers' crops to put out your...
Yeah, so almost all of the time we would do our deployments in a school because they often have little...
Like a playground?
No, not playgrounds, but
you dig up the kids' playground.
Hi and welcome to Wonder, the People Planet podcast brought to you by Geo Co. I'm Holly Cooke, joined as always by my colleague Dr Anthony Reid, and today we have the absolute pleasure of having Dr Kate Selway on board. Kate is with Vox Geophysics and the University of Tasmania and reveals to us how cosmic processes actually let us listen to the Earth and understand how the Earth works. Without further ado, let's get into some modern day exploring with Dr Kate Selway.
You've been to such amazing places in your incredible career. If I list just a few of them, Central Australia, East Africa, the polar regions, including Greenland and Svalbard. But do you have a favourite place to do science?
It's actually a hard question, Anthony, because they're quite separate questions.
They get easier as we go on.
There's a favourite place as a place. And then there's, I guess, the practicalities of doing science in a place. So probably East Africa is probably a good example. So mostly I was working in Tanzania when I was in East Africa, which is a fantastic country, spectacular, unbelievable landscapes, incredible people. Doing science there, or at least doing geophysics there, is really challenging because it's quite densely populated. So for me, to do science, I need space to be able to set out my instruments. So to find anywhere where there's space is really hard.
Digging up some farmers' crops to put out your...
Yeah, so almost all of the time we would do our deployments in a school because they often have little...
Like a playground?
No, not playgrounds. But
you dig up the kids' playground?
Plots where they would grow crops because they would, like the schools would feed the kids lunch and they would grow all the food at the school. So there'd kind of be space and it would be a bit safer in the schools. But there would be kind of for every instrument that we could put in the ground, there would be a solid day at least of talking to various administrators and getting permissions for that.
But you're in Tanzania.
But you're in Tanzania, And then I guess on the other side, that when we were there, we were looking at the East Africa Rift. So you've got like the continent is tearing in two. And so you're looking at these incredible processes and you can see on the surface in the places that you are, there's volcanoes and there's big fault scarps and you can see kind of the surface expression of this process that you're then looking really, really down deep in the earth to see what's going on and what's causing it. So on that side, doing the science there is awesome because it's just continually exciting to see that and then kind of getting back with the people then that geology has a real impact on those people's lives. There's earthquakes, then like there's fantastic rich soil because of all the volcanoes. And so even just talking to these school kids, and we're just these like random white people who've turned up to their school with a bunch of wires
weird
and computers,
instruments.
And trying to explain to those kids what it was that we were doing. But that everyone knows what the Rift Valley is.
Yeah.
So you've always kind of got that link even across such different cultures. So I haven't answered your question at all.
No,
but I think my answer to your question would be that of all the places that I've been, the place I love most is in Central Australia, which is kind of where it all started.
How about that?
I think that there's still, really interesting scientific questions to be asking out there, but just waking up in a swag by a riverbed somewhere with the magpies going, there's actually nothing that beats that. Yeah.
And just on that, so I just heard you say you went to Africa to do geophysics, looking at the Earth tearing itself apart, basically. How geologically does Central Australia top that? How do you top that?
But again, I guess in Central Australia, you've got the fact that those processes happened billions of years ago, the Earth tearing apart and colliding back together, and that we kind of know in Australia that you have these different bits of Australia that used to be parts of different continents and now they're all jammed together. But we don't really know exactly where those boundaries are and exactly how they jam together. And so that was, at least for my PhD days, that was the kinds of questions that we were trying to ask in Central Australia, which are like really big questions that we still don't really know the answer. They're super hard to answer.
Yeah. But that doesn't answer our secret question, which is, why is Kate always at the poles?
That's it. Do you like the cold secretly?
No, I don't like the cold secretly. Or not secretly.
And nothing is about to make sense to anyone.
I mean, so I've been very fortunate in my career. I've just been in Antarctica this summer, and that was my third time in Antarctica.
Amazing.
And then I've also worked a lot in the Arctic. So I've had 3 trips to Greenland, to the ice sheet there, and a couple to Svalbard. So the first time I got to go to Antarctica, I was only just out of my PhD. And it was just kind of an opportunity that was presented to me. And like, I mean, of course you're going to go. So really, I mean, that initial motivation was just all of the, being able to see such unbelievably spectacular things and see penguins and have incredible experiences. And actually the science at that time was kind of looking at similar things that I was saying that we were doing in Central Australia, that again, in Antarctica, you've had places where old parts of different continents have come together. So we were trying to look at similar things there. And I think now, actually, I was reflecting this this last summer, as now it's 15 years since that first time that I went to Antarctica. And so I've had all these other experiences and, you start to get watching. I had a postdoc down with me. It was her first time there, and she was just so excited to be there. She was just so excited by everything. And it was great. And then kind of reflecting on yourself.
Exuberance.
Yeah, that's right.
And we're just the old people here.
That's right.
Not excited.
Not another hole to dig.
Not another penguin.
Penguin.
Whatever.
Oh, that's sweet.
But, I mean, obviously all those things are still exciting. But I think that now the reason that I keep going down now is because of the science now.
Right. It's no longer a fascination with a particular place because it's exotic or whatever.
Yeah, that's right. And then, it's such an incredible privilege to be able to go to places like that. But I've kind of had that privilege and I've had that experience. And that's the science that I go to do now is much more about climate. Actually, I wouldn't go down to do that work that I did the first time, because that's work that you can just equivalent work that you could just go to Central Australia or go out to South Australia or go to West Australia. You can go lots of other places in the world to do that are not so kind of environmentally sensitive to get there. Whereas the work that I do now is, and I try to be quite selective, that I'm only using all of those resources to go there and do work that can have a significant impact on our understanding of climate.
And so I've heard words like geophysics, and now I'm hearing climate and like the work that you're doing. If I hadn't scientifically stalked you for the last couple of years, I wouldn't be able to piece that together.
Scientifically, just to clarify.
Just in an academic sense. But what on earth is I barely understand geophysics as is, let alone when you start saying it can tell us about the climate. So what is that world?
Yeah, so the work that I at least do in Antarctica, there's kind of 2 aspects to that work. So, you think an ice sheet, the Antarctic ice sheet is as much as 5 kilometres thick in places. So you're standing on a totally flat surface, just flat white horizon everywhere.
5 k's down.
5 kilometres down before that's so much. It's really
just such a lot.
Yeah, and bizarre, especially if you've been on the coast somewhere and then you fly kind of to the middle. It happens in Greenland. You fly to the middle of the ice sheet, and you're actually at a really high elevation.
Yeah, actually, your altitude's probably.
Yeah, and it's you kind of need to acclimatise, and it's hard to breathe to start off with. But so bizarre it feels like you're just out in the middle of South Australia in a desert. It's just totally flat and featureless, but bizarre to be actually at such high elevation where you should be up, in Tibet, up a mountain somewhere.
with Anthony.
So anyway, so anything that we need to know about what's happening at the bottom of the ice sheet, we need to use geophysics to see that. And so some things that are super key at the bottom of the ice sheet are especially whether there's any melt water there. So the ice sheet, and then especially at glaciers, because if there's any melt water, then it just acts as a lubricant and the whole thing can slide and collapse into the ocean much more easily. So for then the glaciologists and the ice sheet modelers to know how stable those regions are, one of the really key things they need to know is there any meltwater at the base?
Mm.
So yeah, that's one of the things that we can see with geophysics. So this summer in Antarctica, there's a particular glacier, the Denman Glacier, that we were looking at. And we were looking at how deep the trough of the glacier is, because then we know how much ice is sitting in it. And then also whether there's any meltwater at the base of it, so that then the modelers can put all of that into their models and know how stable it is and how likely it is to collapse.
How deep is it? Can you just cut to the chase? How deep is it?
We don't know. We've got really nice data. I'm confident that our data are going to answer that question, but they haven't. We don't know quite yet.
Impatient.
I mean, from the I guess the modelling that's been done previously, it looks like it's the deepest trough on Earth. So it's 3.5 kilometres thick, which would be deep, which would make it essentially kind of the deepest riverbed on Earth.
Oh, wait, trough is in under the glacier.
If you think of a glacier as a big river and it's just a big river that's made of ice, then kind of the base. Yeah.
3.5, 3.
So if you were to walk from the bottom up the side of the glacier, you would end up, there'd be a 3.5 kilometres worth of up and down you'd have to do. But that entire volume is filled with ice.
Yeah, yeah.
Fantastic.
But that's largely based just on models.
Right.
So that's not based on any direct kind of geophysical measurements of how far do we have to go down before we hit rock.
Okay.
So that's what we were doing, to be like, okay, these models say that it's extraordinarily deep. And if it is that deep, then it's got heaps of ice in it. Mm. So now we'll go and kind of ground truth that and check.
And so there's all the implications that if the ice is melting, the speed of melt, and the impact on climate and sea level, right?
Yeah.
Okay.
Yeah, that's right.
So what I've seen these instruments that you've put out, and what surprises me is how it looks like a box, like a ruggedized box. You chuck in, the tradie would put in the back of their ute, a grey sort of box, and then you open that up and there's a computer in it, of all things, and then you run out these wires. I don't know, how wide, 10, 20, 30 metres?
50 metres.
50 metres.
In each direction.
No wonder you needed a school in Africa. All right, so you run these wires out 50 metres in every direction, 4 directions?
North, south, east and west.
Right. And you have to bury the wires?
We have, at the ends of the wires are electrodes, and we bury the electrodes.
Right. So now explain to me how you can just chuck some wires out and then you can tell something about the deep Earth.
Yeah. So the wires are
because that's a valid question, I got to say.
Putting on the table some skepticism. Come on, Dr. Anthony.
Then we go into Adobe Illustrator and do some reds and blues. No. Yeah. So those wires are really like a massive multimeter, like a voltmeter that you're sticking into the earth. And so that is measuring just electrical, really, really tiny electrical currents that are always flowing in the earth. So entirely natural signals, and we're just putting our wires out to essentially stick a voltmeter across the earth and see that signal. And if you want a bit more detail of how the physics works.
Yes, please, because you could tell from the blank look on my face, he doesn't know what I'm saying.
I've got my coffee. Keep going. Keep going.
No, we need to hear this. Yeah. Please, keep going.
So the signals that we're measuring, well, I guess what we're measuring, our ultimate goal, is to see how electrically conductive the Earth is. So you might have a big hunk of granite that's just rock. You can imagine if you had a granite bench top and you put a battery terminal on either end of it, it's not going to do very much.
Not that exciting.
A big hunk of granite doesn't conduct electricity, so you'll see that as something that's big and resistive.
Right.
But maybe next to it you have, some sedimentary rock that's got some really saline groundwater in it. And then you can imagine, if you're out in a storm when a power line comes down and there's a puddle of dirty water, then you don't want to be touching that puddle of dirty water because you're going to get electrocuted because it conducts the electricity really well. So you'd see that's kind of what we're looking at, that different materials in the earth, some of them conduct electricity well, some of them don't. That's all what we can see. And the signal is, as I say, it's an entirely natural signal that just comes from the earth. So we have...
You're not putting anything into the ground.
Yeah.
You're just measuring it just passively.
You're just like listening.
Yeah. Which is just every now and then I think about that. It's just really that there's all these currents flowing in the earth beneath our feet just all of the time. Like right now, way down 6,000 kilometres beneath us, there's all these currents flowing around in the earth. And they're flowing in the earth because the earth's magnetic field is always kind of being blown a little bit, so that we've got the solar wind blowing on the earth's magnetic field. It's blowing it around a little bit. That blowing magnetic field creates these currents inside the earth. So these massive kind of cosmic processes that I say are always going on. And then just every now and then we go to whatever bit of the earth we're interested in and stick some things in the ground and measure it, and then can say something about what the earth's made of. It's very cool. And as I said, it really is just listening to the earth. These are things that are going on, and we just put our little voltmeter in every now and then and
big voltmeter, big 100 meter.
Yeah, you and these instruments. So you're listening to the earth, but are you in a sense though listening to rocks? Like what's you're sort of listening to how the earth sort of works in it's not electronic. Help me here.
Electric.
In an electric sense. But why would the earth have different conductivities in different places?
Yeah, just because different rocks conduct electricity better and worse. Yeah. So I mean, and I guess as I say that example of if you have some saline groundwater, that's kind of the kind of clearest example, I suppose, that then that's something that's going to conduct electricity super well. But also if you have a place where there's, for instance, a lot of sulfide minerals that also just conduct electricity really well, or a lot of graphite, or a lot of those kind of anything really metallic just conducts electricity well.
And then on that bigger scale, because you were mentioning earlier, like you can see hundreds of kilometres deep. Like we're not actually talking about, you can see that there's a highway tunnel here or some suspicious soil here. We're talking like earth, deep earth stuff. Yeah, exactly. Yeah. And so then I guess a lot of people with a lot of patience do a lot of experiments where they look at minerals, different minerals or minerals with slightly different compositions, put them in lab equipment under really high pressure and temperatures like you would get deep in the earth, and then measure how its conductivity changes, if it gets 100 degrees hotter or you put a little bit more hydrogen in it or whatever it might be. So then thanks to all of those people doing those experiments, then when we do this work, we can say, well, this part of the earth beneath Tanzania here is particularly conductive. So that could mean it's, A, B, and C, that it could, the compositions that it could be there. And then that feeds back into kind of the geology and our understanding of what are the geological processes that could be happening to have brought those compositions in. So it's really, you can actually really tightly link it to geology. I feel like I've always been a bit sus on geophys, but this sounds like really, really, mainly because I don't understand it. But this really sounds like you can talk about the composition of the earth based on these sort of wires that you spiderweb out from a computer on the back of a ute. That's
with that
so
link,
cool.
If you've got that link of knowing, because all that we can see is that, all that we can produce is that model of how conductive things are. It'll be red blobs and blue blobs. And I think that's why I've always kind of wanted to go that extra step in interpreting my models. I've never found that very interesting or very satisfying. So, my PhD out in Central Australia, and I wanted to find where are these old big collision zones. And even back then, I think it was, I can make this model that shows how that this bit over here is more conductive than that bit over there. But unless I know what rocks and minerals I'm expecting to see and what their conductivity is, then my red and blue blobs don't mean anything,
You haven't translated that information to something meaningful in the world in a sense.
Yeah,
exactly. You've just got a model.
Yeah.
Admittedly, these models, they're not just red and blue blobs. Like they're fully three-dimensional images of the subsurface, and you can see, and because you're measuring that one particular property, the electrical conductivity. Yeah. So when you integrate that with what you know about the geology of the surface, that's a sort of interest, right? And other geophysical.
And exactly, and other. So then we might, we can only see how electrically conductive something is, but if you bring that in with some seismic data, so just from one of them alone, I might come up with 3 different options of what something could be, what my red blob could be, but then if it's a blue blob in the seismics, then that cuts it down to, well, it could only be one thing that's red in the MT and blue in the seismics.
Yeah. It's like a big game of guess who.
Yeah, that's right. Yeah. Yeah, but I guess there are people, all the steps require heaps of expertise.
Yeah,
and so there are people who love doing the instrumentation and building better instruments, and there are people who love building better inversion codes and doing all that computer stuff. And that's awesome that those people love doing that.
Thank you, those people.
The wall that you just put up.
That's right. Yeah. And so for me, I'm very happy to take all of their hard work, and then what I'm really interested in is then turning it into something that for me is the interesting part, is what does this tell us about how the Earth works and what it's made of.
So what about Greenland then? So you've been to more or less both poles, maybe not exactly the pole. Did you get to the poles?
No, I've not actually been to either
Pretty
pole,
close to the poles.
Close, yeah.
So you've been to both ends of the Earth. So how similar or different is it? Like when you're in Greenland, you think, wow, this is really Greenlandy ice, or, is that a different experience?
Once you're on the ice sheet and then in that environment where you're away from the coast and it is just that utterly flat white expanse, then it looks
exactly the same.
Pretty identical flat white expanse in both places. The weather's a bit different. So I guess Antarctica is much bigger. So the weather systems tend to be more stable. So like in Antarctica, if you get a storm, it tends to sit there for a week, but then you'll have a week of better weather. Whereas Greenland, weather kind of blows through much more quickly.
Was the fieldwork itself different in those two places as well?
So,
like in terms of the, getting around and whatever.
Yeah. So it is a little bit. So it's then kind of comes back to that kind of cultural aspect, I suppose, that then Greenland's just a country. So to go to Greenland, you have to get permission from the Greenlandic government, but then you can kind of go there. You could just be an ordinary person. You can just fly to Greenland on a commercial flight. If you wanted to, you could just charter an Air Greenland helicopter to take you up to the ice sheet and
check it out.
Hang about for a while,
Right. Geo Co field trip, Ollie.
I'm literally writing notes going, Kate's next special. Take us to Greenland.
Whereas, in Antarctica, it's not just a country, and everything's governed by lots of treaties. So there are lots of rules about doing anything. There's still rules in Greenland. Most of the ice sheets are national parks, so you can't just do whatever you like. But so for me, a lot of my work in Greenland was myself and kind of a mountaineer and another colleague on like snowmobiles, on skidoos, just driving across the ice sheet. So the 3 of us, we had a tent, we had our 3 skidoos, and we would just drive. And we had some support, and we had insurance to get evacuated if somebody broke their leg or something. But we could be quite independent.
Right.
Whereas in Antarctica, everything's you're there. So this work, we were there with the Australian Antarctic Division, and everything's just, I guess, a lot more controlled. Okay, so you're there with the government, and there's just a lot more rules about what you can do.
Even just your comment about
logistics.
Storms, when they come, they sit and they're heavy and they're over a great expanse of land. That's scary. Do you get frightened's the wrong word. Is it a bit cautious? That gives me goosebumps a little bit.
Well, and again, I guess that is part of the reason why there is so much control, because it is a super dangerous environment to be in. And things...
You can die.
You can die just so easily. Yeah.
Or even lose your life.
So many ways to die.
So...
You know that Dumb Ways to Die song? Dumb Ways to Die.
Well, walk off in the wrong direction in Antarctica and you will.
And we're laughing, but that's actually serious. How did you navigate that?
So, I mean, again, I guess with this last trip to Antarctica, essentially the weather's very closely monitored.
Mm-hmm.
And then also on this trip, so we were staying at a camp, and for my work, we basically had to fly either with a helicopter or a little plane to do anything. And they can only really fly if the weather's very good. And so they're getting really good, the Bureau does special forecasts for all of the places that we'll be going to. So you're really only going out anywhere if the weather's really good.
Mm-hmm.
And then when you get out there, the pilots are watching the weather really intently. And if it starts to turn, then you just leave, because it's just too risky. I mean, also every time you go out there, you go out with heaps of survival gear. You'd have kind of a week of food and tents and everything to survive if you did get stuck. But really, no one wants to get stuck.
Don't be putting yourself in that situation.
Yeah. Mm. Whereas then that was quite different in Greenland, because it was just the three of us
swagging
it on the ice.
Yeah.
And so there are storms, and then you just have to kind of make sure you get your tent up
quickly
before the storm hits, and then bunker down in the tent for a couple of days until it goes.
Did you have to do that?
Yeah, a number of times. Yeah. And then just being really careful, even when you're in that situation, of how you set up your tents and making sure, again, so this last trip when I was at this kind of main camp, that there were 30 or 40 of us for most of the time. But when I first got down for 10 days, I was at an ice drilling camp. So that was up on the ice sheet, and there were just 4 of us there. So we had tents, and again, people looking after us, and if, a helicopter could come if it needed to, but not if the weather's bad. And so we had a couple of pretty good storms in that time. And it's because you're just living on snow. So as soon as the wind picks up, the snow's just blowing really, really hard. So you can't see anything. And so these winds, they were not even extraordinary winds, but we could see probably 20 meters. You could see it
That's
2
not
tents away.
Though, is it?
But yeah, and so we would have what they call a blizz line, so a rope that's put up between all the tents, so that if you need to go to the toilet, then you can find your way back to your other tent.
So many things to think about.
There are days where I need to pee every 20 minutes. I would just let the team down if I was out in Antarctica.
You do also have some pee bottles that you can...
Oh, stop it!
But yeah, in those situations, and so you find that everything's set up that you're going to be safe.
That's wild.
But if you got turned around and you lost that blizz line and you just were facing in the wrong direction, it is you do have that thought of, wow, you could die so easily.
Wow.
And if you just wander off, again, 20 meters in the wrong direction, people can't find you because you're just lost in all of the white. So they're super. They're not environments that we're supposed to be.
We're evolved to be in.
No, it's really dangerous. Yeah,
I can see why Central Australia holds its attraction to you now. Now that you put it in that context, I don't know if geophysics is worth losing my life for.
Those stupid little wires.
Important questions though they are. And so, Kate, what's next? How are you taking this geophysics that you've collected? What's the process that scientists like you go through to take it to its completion?
Yeah, well, I think as I was saying, so I mean, this data we've just collected in Antarctica, so it's quite a long process then of making sure that the data is really clean and we've processed it properly, and then we've got some models that are really, really reliable and we can really trust. And then, then that next step of bringing in all the other data and understanding what it means. So one cool thing about the work across the glacier in Antarctica was that we also had people collecting gravity data and seismic data at the same time. So then that lets us do what I was saying before, that, if one of those doesn't give us a really clear or unambiguous answer, that we put it all together and then we have really a fantastic data set. So we'll put all of that together. But, then I think about this a lot with the polar work, that, so I guess the end, scientifically, the end of that will be that we have an understanding of how deep that trough is and how much water there is at the bottom. So then people can feed that into their models of how stable the glacier is and what its potential sea level rise is, which is good. But I also think, we know that the ice sheets are melting. It's also not like Albo's sitting there being like, I've just got to wait for Kate's results from the Denman Glacier to know whether to approve that next coal mine or not.
That was great.
So
great.
And it's something that I think about a lot with that work, because I say it's a huge amount of resources, and you're burning a lot of fossil fuels to be going and doing that work.
Mm-hmm.
So I think, and I struggle a lot with whether I can really justify going down and doing that science. And for me, so then the other part of what to do with it is to kind of use the platform that it provides as well, to then be able to, school kids always want to hear about your trip to Antarctica or your trip to Greenland, to do those sorts of things. This work that we were doing on the Denman was part of a really big campaign. So that does have the potential to, just because it was a big investment from the Australian government, to then kind of something that can get in front of politicians' faces and hopefully have some kind of policy implications. And just use it as a platform to be able to talk to people about the fact that, the ice sheets are melting and this is really bad and we do really need to do something about it. So for me, that's part of what I hope to do with it as well.
Fantastic. Thanks, Kate.
Thank you, Kate. You're a legend. Thank you so much.
Thanks.